This section is about advanced linear regression. So what we've done so far is we've looked at sample data and found a regression line where y hat, our predicted value of y, is equal to b0, that's our intercept, plus b1, that's our slope, times x. But just like everything else we've done in this class, you have your population, which is everything you're interested in, and then you take a small sample. So what we've looked at so far is just our small sample. Okay? And there's a difference between your sample statistics and your population parameters. So what we can do is we can think about having a model that's true for our entire population, where y would be equal to, notice we switch from a little b to what we call a beta. So this is a Greek beta. So we'll do beta 0 plus beta 1 times x. So beta 0 refers to, instead of a b0, is our population intercept. And instead of a little b1 for our sample slope, we'll have beta 1 for our population slope. Plus, and notice this little epsilon. This is Greek for epsilon. So there's a true population slope, beta 1. We don't know what it is because we don't have all of our population values, but it's there. We just don't know what it is. We have a true population y-intercept, beta 0. So again, the b is for our sample, the beta is for our population. And there's some error component, epsilon. Why do we need an error component? Well, we wouldn't expect every observation for any x value to have the exact same y value, because there's too many other things that affect it, and there's just natural variation in any population. But we can predict kind of our mean or average, and then we can let our individual values vary. So what do I mean by that is if we were to look at people and graph the calories they eat per day and their weight, we wouldn't expect everyone that eats 2,200 calories a day to have the exact same weight. We would expect there to be some variation. So your average would be where the line is, but then Susie might be a little bit above it, and Mark might be really tall, and so he might weigh a bit more, and Joe weighs a bit less, and Ryan exercises and works out a lot, he weighs a lot less. Okay, or for the people that eat 2,600 calories a day, notice the whole mean shifted up, but there's still some variation around the line. Okay, or at 3,000 calories, again the mean shifted up, but there's still a lot of variation in individual people around the line. So what epsilon does, or that error, is it accounts for the individual people. So we're saying we can predict this line, okay, or in our population there would be a line that would kind of go through the averages at each part, but the individual people are going to be off the line a little bit, and that's why you need the error component. So what we can do is we can predict the average y value for any given x, so the average would be like on the line. Or we can also predict an individual response for a certain value of x. But you're not going to be as accurate since individual values can vary. Because, again, the most important thing to remember is individual y values can vary. So when I make a prediction, it's always on the line. So what's on the line, that will be close to the average. But the individual people, I can predict what John's weight will be. But I probably won't be as accurate because he probably won't be on the line. So when we mean the individual y values can vary, for any given x value, you see some variation in the y values. So again, for this 2,200 calories, we see quite a bit of variation from Mark down to Ryan. They change quite a bit. But the individual y values for any given value of x should follow a normal distribution. So of all the people that eat 2,200 calories a day, for Mark, Susie, Joe, and Ryan, if you took the weights of those guys and the thousands of other people who all eat 2,200 calories per day, all of those weights should follow a normal distribution. And if you look at everyone that eats 2,600 calories a day, Lance, Jill, John, Sally, and the thousands of other people that fit in that category, all of their weights should also follow a normal distribution. And the standard deviation of that normal distribution for each of the sets should be the same for all the values of x. Or, again, if you were to look at kind of the variation in y values at every x value, that variation should be about the same, or the standard deviation at each point should be about the same. We can think of each y value for a specific x as y equals again, our intercept for our population plus our slope for our population times x plus epsilon I, where again, epsilon is our residual. So our residual is equal to our observed minus our expected or our predicted. So we just introduced the new notation there, but it's the same formula we had before. Residual just equals the observed or actual minus the predicted. And the residuals are assumed to be independent and normally distributed with a mean of 0 and a standard deviation of sigma. So when we want to estimate our regression parameters, we can estimate our true regression line, which is y equals our intercept plus our slope times x plus some error term for our population. And we estimate it with our sample regression line. So y hat equals b0 plus b1x. So let's just make ourselves a note of our notation. So for our sample, we use b0 and b1. For our population, we use beta 0 and beta 1. We can also estimate our population standard deviation of all of our residuals, which we would call sigma, with S, which is our average squared residual. So the way they found S for linear regression is slightly different from our normal standard deviation. You just take each residual and square it, and then take the average, which is pretty much the same thing as before, just slightly different. We often call S the standard error of our model. So for example, I generated 4 different data sets, each with n equals 25. They come from a population where my population intercept is 12 and my population slope is 5. And the population standard deviation of the residuals is 10. So the true equation of our population line is y equals 5x plus 12 plus some error term. So you can see here I generated 4 different data sets. My first data set looks like my points are pretty close to the line. I have a very high r-squared value of 0.95. My sample slope is 5.28 and my sample y-intercept is 8.85. So let's just remind ourselves. So the population slope is 5. Population intercept is 12. And population standard deviation is 10. So population intercept, population slope. Okay, so I got 5 for my sample slope, but my population slope was 5. Or 5.28 for my sample, my population was 5. My population intercept was 12. This time I only got almost 9 for my sample, and my population standard deviation was 10, but my sample standard deviation was 7.39. And if I zoom out a little bit, you can see that every time for my 4 sets, my slopes change a bit. They vary from 5.28, 5.2, 4.62, and 5, but they're all fairly close to my population of 5. For my intercept, that was supposed to be at 12, I'm at about 9, 6.5, 14, 15. That one actually seems to change a lot more. My slopes were pretty close. My intercepts changed a lot more. And then for the standard deviation of the residuals, we're at like 11, 10, 8, and 7, whereas my population was 10. So we get different values for our line of best fit for each sample. The estimates for the slope vary from sample to sample, but they should all be close to our population slope of 5. The estimates for the y-intercept will vary from sample to sample, but they're close to beta 0, which is 12. And the estimates for our population standard deviation vary, but they should be close to our population standard deviation of 10. So with that in mind, we know the slope of the line for our sample data, but we're often interested in the slope of the line for the population of all the values. So what we could do is we could find the confidence interval for our slope. Now remember, a general form is estimate plus or minus a critical value times the standard error of your estimate, or standard deviation of your estimate, depending on which one you have. So our confidence interval for our population slope would be our sample slope plus or minus our critical value, t star, times the standard error for our slope. So this is standard error for the slope. And t star is our critical value from a t-distribution, but this time it has n minus 2 degrees of freedom. So it's different from our t-test because it's a different procedure. But we're not really going to worry about doing any of that by hand. We're going to use our megastat output. So this is what your output will look like in megastat. Each computer program is different, of course. Let's look at some things. So I see r squared and r. That's going to be your correlation in r squared. You have standard error. This is S for your entire model. It's the standard error for all of your residuals. You have your sample size at n equals 16. And your response variable, or your y variable, it tells you was fact. And then down here, you'll have a line that says intercept, and then you'll have a line for your x variable, NEA. And that line there will be everything that talks to you about your slope. So the coefficient for the intercept will be the b0, so my y-intercept is 3.5. The coefficient on your slope row is going to be your b1, so my slope is negative 0.0034. Then it'll give me my standard error for my slope. So standard error on the slope line is standard error for b1. And also notice, what does it give me? A confidence interval. So all you have to do to find a confidence interval is just read it off the line. So for this example, a study was conducted to see if fidgeting or non-exercise activity could help reduce fat gain in kilograms. Here are the results. So again, you can see it tells me my y variable is fat. I have r squared, I have r. This intercept is the first line, and then your slope is the second line that has the name of your x variable, NEA. So what are your response and explanatory variables? So my explanatory, notice explanatory has x in it, that's your x variable, is going to be the non-exercise activity, NEA. And the response, or your y variable, is going to be fat, because it said fat is your dependent variable. So use our plus to determine if linear regression would be appropriate here. Well, it looks like I could have a line going down through that, and that looks linear enough. My residual plot against my x variable looks random enough. And my normality plot looks straight enough. So they all look good. So yes, we're good there. What's our equation for the linear regression line? So again, we just have to come up and look at our results. So y hat is going to be equal to our intercept of 3.5 plus our slope, which is actually negative, so we can change that to minus 0.0034 times x. Now, I prefer to go ahead and write it with words. So, fat is our y variable. So we could do our predicted fat equals 3.5 minus 0.0034 times NEA. What is our estimate for our population intercept? So our estimate is just this intercept, or B1. So our best estimate for the population intercept is our sample intercept of 3.5. To interpret it, remember a y-intercept means if x equals 0, what is y? So in our case, we would say if NEA is at 0, then we predict fat of 3.5. What's our estimate for our population slope? Well, our best estimate would be our sample slope of negative 0.0034. Let's make a note. This was for my intercept. This is for my slope. And since slope is rise over run, we interpret slope as if x goes up 1, y goes up blank. So in our case, if any A goes up 1 unit, then we predict fat will, let's see, that's a negative, so it will go down. Will go down 0.0034 units. So as you do some non-exercise activity, but just as you're more active, your fat should go down a little bit, which makes sense. Let's predict the mean fat gain for all people with the NEA level of 101. So all we have to do is plug 101 into NEA. Into our equation. So our predicted fat will be 3.5 minus 0.0034 times 101, which is 3.16. Notice this said the mean fat, so we really found we predict that for all people with an NEA of 101, the average will be 3.16. Now it says predict the fat gain for a single person, but still with an NEA of 101. Well, I'm still going to do the exact same thing. I'll do 3.5 minus 0.0034 times 101, which still equals 3.16. So this means we predict that if, I'm just going to make up a name here, if Sally has a NEA level of 101, then her fat will be 3.16. Notice whether I'm trying to predict it for one person or the average for all of the people, I do the exact same thing. But which one would be more accurate? The average is probably going to be more accurate because individual people tend to vary quite a bit. Let's see, what was the correlation and interpret it? So come back up. Correlation, notice here it tells me R equals negative 0.779. Let's see, that is a negative value, so that means it will be a negative association. And it's pretty close to -1, so I'd say it's a fairly strong relationship. So the points should be fairly close to the line. Now it wants us to interpret R squared. Well, that's not too bad either because you just come up, find the thing that says R squared, so 0.606. R squared equals 0.606. Remember, R squared tells you what percent of the variation of the y values you can explain with your line. So it's what percent of y, let's see, variation in y you can explain with the line. Okay. So we can explain 60.6% of the total variation in the y values with our line. That's not great, not horrible. I like to have it a little bit higher. And finally, find a 95% confidence interval for our slope and interpret it. Well, for this, all we have to do is come up here and say, okay, where does it say confidence interval? The hard things, make sure if you're interested in slope, slope is always that bottom line, so we're interested in this confidence interval of negative 0.005 to negative 0.0019. So we're at negative 0.005 to negative 0.0019. Let's see, so I could say we are 95% confident that the population slope is between negative 0.005 and negative 0.0019. This means we are 95% confident that if NEA goes up by 1, then the fat will go down between 0.005 and 0.0019.